Okay, today's topic in Unit 4 is scientific notation. And when we talk about scientific notation in math class, that might sound a little weird to be talking about something scientific in a math video, but think about what science does. Isn't science designed to help us understand the world we live in and to help us learn about the universe that we're part of? And in order to understand the world we live in and the universe around us, don't we need to count things and measure things? And isn't math what allows us to count things and measure things? So the question really is, can you even do science without math? And of course the answer is no, you need math to do science. And scientific notation is math's way of helping science count things and measure things, especially really, really big things and really, really small things. So, speaking of really, really big things that you might try to count, have you ever been camping or something and been someplace kind of remote where there's not a lot of city lights and you looked up into the sky at night and you were amazed by the number of stars in the sky? Have you ever had that moment where you look up and it's just kind of this awesome canopy of millions of stars, or I don't know if it's millions? How would you know how many stars there are? That's a great question. How many stars are there? If we were going to count them all, that'd be a pretty tedious job. But isn't that kind of what science does? Yeah. So the question is, how many stars are there in the universe? And we don't know. Humanity has never found the exact answer to this question. But through increased technology and telescopes and we've gotten smarter as a human race, we've been able to come up with some pretty good estimates. The latest estimates on the number of stars in the universe are that there are this many stars. Oh, no, wait. There are this many stars. That's a 3 with 23 zeros behind it, and the name for this number is 300 sextillion. There are 300 sextillion stars in the universe, approximately. That's a lot, okay? That's a huge number. And maybe that number seems kind of dumb and ridiculous to you, like that's just so big, I can't even comprehend what that means. Or maybe it's not that the number itself is dumb, maybe that number is so big that it kind of makes us feel dumb because our minds can't comprehend a number that large. But it's the truth. That's approximately the number of stars in the universe. And when you're doing science, you have to deal with big numbers like that. And sometimes in science, you have to deal with really, really tiny things. Like instead of gigantic, massive stars, you're dealing at the atomic level or the subatomic level. And you might ask a question like this: what's the mass of a single electron? In this case, the mass of a single electron looks like this. 0.0000000 something. Okay, here it is for you. That's a bunch of zeros. That's a really, 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 really tiny, tiny number. Okay? And so in science, we deal with humongous numbers, and we also deal with really tiny numbers. Numbers that are kind of inconvenient to write out. Here's another example. The distance that light can travel in 1 year is called a light year, and in kilometers, that's a huge number of kilometers. Or the distance from our sun to the nearest star in the universe. Okay, we're talking humongous numbers, and when you think about it, these numbers are just crazy. Our brains can't really comprehend numbers this huge and numbers this small, and numbers like this that take a lot of zeros to write out because they're so big or because they're so small are kind of tricky to deal with in math. So let's take the number of stars in the universe, for example. 300 sextillion. Okay? There's an easier way to write crazy, crazy long numbers like this, and that easier way to write it is called scientific notation. Scientific notation is basically just like an abbreviation. Okay? Like how in English, we sometimes write OCT instead of October, or USA instead of United States of America, or Mr., we abbreviate MR, or other things like that. Okay? So scientific notation is a way to abbreviate long numbers instead of abbreviating long words or phrases. And in this case, the way to abbreviate the number of stars in the universe is to write it like this: 3 times 10 to the 23rd power. And that's a nice, short, compact way of writing a number that otherwise would have taken a long time to write out. But in order to understand how scientific notation works, we've got to understand 10 to the 23rd power, and we've got to understand how powers of 10 work. So let's review. Okay, I've got some powers of 10 here. We should know that 10 to the 0 power is 1, because anything to the 0 power is 1, right? Yeah. What about 10 to the first power? Well, anything to the first power is itself, so that's just 10. And these aren't that difficult. 10 squared is 10 times 10, that's 100. 10 cubed is 10 times 10 times 10, so that's 1,000. And if you times that by 10, you get 10 to the fourth, which is 10,000. And if you times that by 10, you get 10 to the fifth, which is 10 times 10 times 10 times 10 times 10, which is 100,000. And I think you might be noticing something here. Look at the number of zeros in these. 10 to the fifth has 5 zeros. 10 to the fourth has 4 zeros. 10 to the third has 3 zeros. 10 squared to the second power has 2 zeros. 10 to the power of 1 has 1 zero, and 10 to the 0 power has 0 zeros. And that's kind of a cool thing, because if you wanted to write a really, really long number in math, you could write it as 10 to the something power. And that's kind of how we do scientific notation. So in this example, 100 billion can just be written as 10 to the 11th power, which is a lot easier than writing 100 billion. All right, what if we do some other things with the powers of 10? We already know 10 to the 1 power is 10 and 10 to the 0 power is 1. What about 10 to the negative 1 power? Well, that means 10 to the power of 1, but the negative tells us that it goes in the denominator. By the way, I added a little decimal to that 10 to the 0 power, and you'll understand why in a minute. Okay, back to 10 to the negative 1. That's 1/10. And there's another way that we can write 1/10, right? We can write it as a decimal, 1/10. Okay, what about 10 to the negative 2? Instead of 1 over 10, that's going to be 1 over 10 squared, right? 1 over 10 times 10, which is 1/100th. And we can write that as 1/100th in decimal form as well. And it's not going to be shocking when I tell you that 10 to the negative 3 is 1/1000th, which you can write as decimal as well. And now, when we compare all of those decimals that we just calculated and line up the decimal points, notice there's a little bit of a pattern here. Okay, if you line up the decimals, notice the 1 keeps moving backwards, doesn't it? So every time we lower the power of 10, every time we lower the exponent, the 1's move backwards, and every time we raise the exponent, the 1 moves forward. Or another way you could do this is, what if you line up the 1's? Now what you're going to see is, each time, it's not the 1's that are moving, it's the decimal that's moving to the left, and then to the left, and then to the left, and to the left, and you see that the decimal moves each time you change the power of 10. Alright, so, keeping that in mind, let's evaluate what is 10 to the 7th power. Remember the trick. The number of zeros should be the same as the number of the exponent. Okay, and then evaluate 10 to the negative 4th power based on what we just said about the powers of 10 and decimal points. And if you need to rewind for a minute, you can rewind and review what we said about the powers of 10. Okay, scientific notation then. What if you have 10 billion? Then that would be 10 to the 10th power because you can just count the zeros on there. Okay, the zeros there's 10 of them. But what if you had 70 billion? If you had 70 billion, isn't that 10 billion times 7? Yeah, it's just 10 billion times 7. So in this case, since 10 billion is 10 to the 10th power, couldn't you make this 7 times 10 to the 10th power? Instead of writing it out as 70 billion? Yes, you could. And what we just did is we took the standard way of writing 70 billion, the standard notation, and we just changed it into scientific notation. Okay, so scientific notation is a shorter, abbreviated way of writing the standard way that we write numbers. Here's a better example. Okay, what if I had, oh boy, this is 9,370,000,000,000. Okay, that's the standard notation way to write it. And there's 1 trillion, but really the number in blue is 1 trillion times 9.37. So if 1 trillion has 12 zeros, that means it's 10 to the 12th power. And if 9,370,000,000,000 is 9.37 times 1 billion, then we could write it as 9.37 times 10 to the 12th. And that's a nice, compact, abbreviated way of writing this big, huge number in scientific notation. All right, here's what else you need to know about this. The rule for scientific notation is you can only have 1 digit in front of the decimal. So we're not going to take the 9 and the 3 and the 7 and make it 93.7 or 937 or 0.937. We're going to put the decimal right between the 9 and the 3 because you're only supposed to have 1 digit in front of that decimal place. Okay? One more example. If you had 60,000, that feels a little bit nicer and more manageable, doesn't it? In this case, count the zeros. There's 4 of them, so wouldn't this be 6 times 10 to the 4th? Yeah. Oh, that wasn't very difficult at all, was it? How about 89,100,000? Can we count again? We know the decimal needs to be between the 8 and the 9, so we're going to count the number of spaces that it takes to get us there, and we've got 1, 2, 3, 4, 5, 6, 7 spots, so it's going to be 8.91 times 10 to the 7 power because of the 7 spots. And the decimal goes right between the 8 and the 9 so that we only have that 1 digit in front of it. Okay? Here's 123 million. We're going to count the other way this time. It doesn't really matter which direction you start with. There's 8 spots there. We're going to put the decimal between the 1 and the 2, so there's only 1 digit in the front, and we're going to make it 10 to the what? 10 to the 8th, because we counted 8 spots. Not bad, huh? Okay, so try it now. Convert this number to scientific notation. Okay, what if I gave you a number in scientific notation? Could you then write it in standard form? Sure. Remember, we're going to take 431 and write it as 431, and then we're going to count 6 spots because it's 10 to the 6th. So there's 1, 2, well, I guess I'll just go 3, 4, 5, 6, but what about those blank spots? Oh, that's not a problem. I can just put zeros there. And now I know that 4.31 times 10 to the 6th power is really 4,310,000. That's going from scientific notation to standard notation. Okay, so now you try this. Try writing this number in standard notation. Use that exponent of 5 and move that decimal 5 spots. Okay, what if we have little numbers, little tiny small numbers, like 0.000000045? You can still take that kind of a standard notation tiny number and count the spots all the way here because we want the decimal between the 4 and the 5 so that we can go 4.5, because remember, scientific notation has to have only 1 digit in front of the decimal, so we want that 4 or 5 to be 4.5, and then we just count how many spots we went to get to that 4 and 5 middle. So we counted 1, 2, 3, 4, 5, 6, 7, 8. Okay, we put the decimal there, so it's going to be 10 to the 8th power. 10 to the negative 8? Oh, notice on this one, the number is negative because we moved the decimal backwards, didn't we? Or you could say that it's negative because this is instead of a really, really big number, this was a really, really small number. So really big numbers in scientific notation have really big exponents. Really small numbers in scientific notation have really small exponents, or what we would call negative exponents. Interesting. Let's try another example. What if you had 0.0000678? 1, 2, 3, 4, 5, and we're going to stop there, right? Because we want it to be 6.78 times, well, we counted 5 spots, but we went backwards, so it's 10 to the negative fifth. Yay! Oh boy, that's a lot of zeros. But we can do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 3.45 times 10 to the 10th, right? Oh no, 10 to the negative 10th because we counted backwards. Okay, you try it. Write this tiny number in scientific notation. Remember to put the decimal point between the 7 and the 6. All right. We finally did it. We did it. Thanks for listening, guys. I know this one was tricky. Feel free to rewind. Feel free to rewatch. Feel free to write down questions, and we'll talk more about this in class tomorrow.